Am I audible, students? Are you able to listen?
Yes, sir.
Yes, sir.
Right. In the previous class, I had given the definition of divergence theorem, that it is defined as the vector A. Divergence of vector A is defined as the outward flow of flux, that is closed surface integral A dot ds per unit volume divided by delta V, as delta V tends to 0 over a closed incremental surface. Let us consider a point P, and we want to find the vector A at this point P. Okay, we are applying the divergence theorem for the vector A at this point P, right? We are considering that this point is enclosed by a closed surface. This point P is enclosed by this closed surface. Okay, it has front surface, it has front surface, back surface, side surfaces, left and right, and top and bottom surfaces. Okay, front surface, back surface. This is the left surface, the right surface, top surface, and the bottom surface. Okay, accordingly, it has the coordinates. This is dx along the x direction, right, and dy along the y direction, and dz along the z direction, right. Surface integral in equation 1 is obtained from, what is the equation 1? This is our equation 1. We want to find the closed surface integral of the vector A with respect to ds, is it not? That is, here if you want to obtain the surface integral, then we have to integrate A dot ds, that is, we have to integrate A dot ds with respect to front surface, then over the integral of back surface, over the integral of left surface, right surface, top surface, and the bottom surface, is it not? We have to integrate this vector with respect to the surface, considering the integral of the front surface, integrals of the back surface, left, right, top, and bottom surfaces. That is, front surface integral, back surface, left surface, right surface, top surface, and the bottom surface, is it not? If we integrate all these surfaces, then we'll get the closed surface integral of the vector A with respect to ds, correct? Let us take this as equation. A three-dimensional Taylor series, a three-dimensional Taylor series of vector A about point P. How do we define the Taylor series, students? You have studied Taylor series in your mathematics. Taylor series is the sum of infinite terms in which each term is a function of the vector. Right? Taylor series of a function is the sum of infinite number of terms, where each term is the function of the given vector. For example, here a of x comma y comma z. Okay, this is the origin. This is the initial term, origin, about the origin. Ax of x naught comma y naught comma z naught plus, it is the function of the a. It is a function of a, that is x minus x naught. Yes, please.
Sir, Ankita is trying to join, sir. Please allow her.
1 minute. I will admit her. I have admitted her. Right. I'll mark her attendance also later. Sorry, something wrong here. Okay. Right. A three-dimensional Taylor series of the vector A about the point P is the vector, that is that if you want the Taylor series expansion of this A about the point P, we are finding the vector A about the point P. For this, we are applying the Taylor series. If I apply the Taylor series, then the expansion is the initial term, that is the about the origin ax, or the vector A about the origin, that is x naught comma y naught comma z naught, plus the difference between the present point and the origin. What is the present point? This present coordinate is p of x comma y comma z. Okay, from the origin this is x naught. Okay, if I take this corner, it is x naught from the origin. If I consider up till the point P, then it is x. So what will be with respect to the box, students? It is x minus of x naught. Okay, from this origin to this corner of a box, if I consider it as x naught, and from this origin to the point P as x, then what will be the respect to the box? It is x, that is origin to the point P, minus x naught, origin to the corner of the box. Okay, that will give the coordinate of the point P with respect to this box, with respect to this box. Correct? That is what we are writing here. Plus x minus x naught, that is the Taylor expansion, dou ax by dou x. That is, it is a function of, it is a derivative of the function. Okay, what is Taylor series? Taylor series is consisting of sum of infinite number of terms where each term is the derivative of the function, given function. Okay, so here it is a derivative of the given function a or ax, that is x minus x naught into dou ax by dou x at the point P, plus similarly we have to write for the y and z points. Okay, for the y and z points it will be y minus y naught. This is y. If I consider from here to here, origin to this, it's y. Then corner, if we take it as y naught, then y minus y naught. That will give the distance from the box side to the point P. Okay, y minus y naught. Similarly, for the z coordinate, it will be z minus z naught. For y, it is y minus y naught. Okay, for z, it is, this is vertical, z is vertical, this is our z axis. So this is z from this, then minus z naught, that will give the coordinate of the point P with respect to the surfaces, side surfaces. Okay, that is plus y minus y naught of dou ax by dou y, that is a given vector a. That don't take it this ax as ax coordinate, it is not like that. It is a given function. Given function is a. If it is confusing for you, then just you can take it as a. Okay, plus y minus y naught of dou ax by dou y with respect to point P, plus z minus z naught dou ax by dou z with respect to point P, plus the higher order terms. Higher order terms will be the second derivative, third derivative, like that. Higher order terms. Okay, right, for right now, for time being, we'll write them as plus higher order terms. Take it as equation 3. For the front side, x is given by x naught plus dx by 2. For the front side, that is this surface, front surface. Okay, what is our x? It is x naught, that is from this point to origin and the corner of a box, plus this distance, that is the front surface, dx by 2. Dx by 2. From this to this corner is dx. So point P, we are assuming it as it is exactly at the center. Point we are assuming it as exactly in the middle, exactly in the center of the box. So what will be the distance from the front surface to the point P? Dx by 2. From one corner to another corner, this side is dx. Correct? If I want in terms of x, then it will be dx by 2. Right? That is x naught, this distance, x naught, this distance, plus this dx by 2. Right? That is what I am writing. X is equal to x naught plus dx by 2. And ds, what will be the area, students? Area will be for the front surface, this is a front surface, that is dy into dz. Length into breadth. Dy is the length, breadth is dz, into the vector ax, that is the direction. Ax, unit vector ax in the perpendicular direction, that is ax direction. Area is given by ds is equal to dy dz into ax. Then the double integral, that is for the area, we have to take the double integral. Front surface, a dot ds is equal to dy dz. This is our a, correct? If I integrate it with respect to ds for the front surface, that is, what is a, students? A is this function, that is ax x naught comma y naught comma z naught, that is I have written here ax of x naught comma y naught comma z naught, plus this is our ds. Okay, ds is dy dz into ax magnitude is 1, that is why we have taken it as dy into dz. Then this is ax of x naught comma y naught comma z naught, write it as it is ax of x naught comma y naught comma z naught, plus, see here, x minus x naught. If I take x naught to the LHS, what it will be? If I take x naught to LHS, what it will be? Here in this term x is equal to x naught plus dx by 2. Dx by 2, correct?
Sir,
X minus x naught. Yes, please.
sir, minus x naught, sir.
Correct. Minus x naught. You are right. X minus x naught, that will be equal to dx by 2. Yes or no? X naught, if I take to the LHS, it will be minus x naught. X minus x naught is equal to dx by 2. Am I right? Therefore, here I am writing instead of x minus x naught as dx by 2. Dou ax by dou x at the point P plus higher order terms. Higher order terms. Correct. This is for the front surface. Next, I have to write for the back surface. Okay. For the back surface, what are the changes here, students? This area will be ds is equal to dy dz minus ax because it's a back surface. Let us look to the figure. So it is back surface here, opposite side. Okay, so it will be dy dz minus ax. Then the coordinate of this point P with respect to the box is x is equal to x naught minus dx by 2. Now x naught we have to take from the origin to this corner, not this first corner. Getting the point here? Because we are considering the back surface. So x naught will be from the origin to this corner here, this corner, what I am pointing, this pointer. Okay, so that is our x naught. Then this distance is dx by 2. X naught minus dx by 2, that gives the coordinate of the point P with respect to the box. Correct. For front surface, if it is x naught plus dx by 2, for back surface it will be opposite, x naught minus dx by 2. Hence I am writing here for back side it is x is equal to x naught minus dx by 2. ds is equal to dy dz into minus ax because it is opposite side, unit vector will be in the opposite direction. Then the back surface, that is this formula. This formula we are integrating each integral we are finding, that's for front surface, back surface, then front plus back, left right integral, then left plus right, top and bottom integrals we are finding, then we are adding top plus bottom, and finally we are adding all these and finding the closed surface integral of a dot ds. That is how we are proceeding here. For the back side, x is equal to x naught minus dx by 2. So it will be ds is equal to dy dz into minus ax. Then we have the back integral of a vector a with respect to small surface ds, that is this is ds is equal to dy dz into minus ax. Minus ax unit vector is 1. It is minus dy dz. A, what is a? Again the same thing, go back to the Taylor expansion. A is ax of x naught comma y naught comma z naught, that is ax of x naught comma y naught comma z naught. Then x minus x naught. Now let us see what is x minus x naught. This is x naught minus dx by 2. Correct? X is equal to x naught minus dx by 2. If I take x naught to the LHS, it will be minus x naught. X minus x naught will be minus dx by 2. X minus x naught will be minus dx by 2. Write it. That is x minus x naught will be minus dx by 2 into dou ax by dou x. It is minus dx by 2 into dou ax by dou x at the point P plus the higher order terms. Okay. Next, what we are doing is we are adding front integral plus back integral. We are adding front integral plus back integral. Anyhow, we have to add all the 6. That is front, back, left, right, top, bottom. First, we are adding front plus bottom, back, then left plus right, then top plus bottom. Then we are adding all these 3 to get the closed surface integral a dot ds. Here, students, the front plus back. Now we have to add the front surface with the back surface. If I integrate the front surface with respect to the back surface, that is, if I take the sum of front surface integral a dot ds plus back surface integral a dot ds, that will give me, look here, what is the front surface? Front surface is dy dz into ax of x naught comma y naught comma z naught. Correct? So this, then here what term we are having? Minus ax of x naught comma y naught comma z naught. So both will get cancelled. This is plus dy dz ax of x naught comma y naught comma z naught. Then this will be minus dy dz ax of x naught comma y naught comma z naught. Both will get cancelled. Next, we'll go to the next term. Dy dz into dx by 2. dy dz dx by 2 dou ax by dou x, correct? Then here what we'll get, let us check, minus into minus, it is plus, right? Here also we'll get the same term, minus into minus is plus, minus dy dz into minus dx by 2, it is plus. Therefore dy dz dx by 2 dou ax by dou x. There also we are getting the same, that is dx dy dz dx by 2 dou ax by dou x. Then here also plus dy dz dx by 2 dou ax by dou x. Now if we add them, half plus half is 1, or 2 is the denominator, so in the numerator also we'll get 2 dx dy dz divided by 2, that will give us dx dy dz, okay, plus dy dz dx by 2 plus dy dz dx by 2, it is how much? Half plus half is 1, correct? Or 2 is the LCM, if you add the numerators, it will be 2 dx dy dz, 2 and 2 will get cancelled, 2 in the numerator and 2 in the denominator will get cancelled, will get only dx dy dz, correct? That is dx dy dz dou ax by dou x at the point P plus the higher order terms. Let us take them as equation 4. Okay, I hope you are following here, students. Yes, students, are you following here? Any difficulty up till now? Yes,
No, sir.
following, right?
Yes, sir.
Okay,
Yes, sir.
right. Similarly, let us find the left surface and the right surface integral. Left, by taking similar steps we'll obtain, we'll write the directly, not necessary to again use the Taylor series and write it. Directly we can write it. Left is double integral, that is area, a dot ds, plus right integral of a dot ds, that is double integral, that is equal to dx dy dz into this one. How we'll get this one here? See, this is dou ax by dou x, that is front and plus back, because if you look into the surface, we are taking the coordinate of the x. Sorry. We are taking the coordinate of the point P with respect to x. Okay. So when we take the left side and right side, it is y coordinate, this one, left to right, this coordinate, y coordinate it is, correct? Therefore, in this term, we will get dou ay by here, front plus back, then left plus right will get dou ay by dou y with respect to point P plus the higher order terms. For front plus backs, what we are getting? Dou ax by dou x at point P. For left plus right, what we are getting? Dou ay by dou y at the point P plus the higher order terms. Okay. Next, for top and bottom, what is the coordinate we are taking for top and bottom? Let us look that. Top is here vertical direction, it is z, 0 to z, correct? Vertical, so it will be top means it is with respect to z. Therefore here the term that we will get is dou az by dou z for the top plus bottom. Double integral of top surface integrals a dot ds plus double integral of for the bottom integrals a dot ds, that will be dx dy dz dou az by dou z. It will be dou az by dou z at the point P plus the higher order terms. Okay, let us take it as equation number 6. Now if I put equations 4, 5, 6 into equation 2, if I substitute equations 4, 5, whatever we have got for front and back, then left and right, top and bottom, equations 4, 5 and 6, if I substitute in equation, what is our equation 2, students? This is our main equation, correct? If I substitute them, then what will happen? Let us check that. That is, we will be getting, put equations 4, 5 and 6 in equation 2, and note that into closed surface integral a dot ds, if I substitute, what are the terms we have got? Front plus back, dx dy dz dou ax by dou x. Then for left and right, dx dy dz dou ay by dou y. Okay. Then top and bottom, dx dy dz dou az by dou z. If I add all these, that is equation 4, equation 5, equation 6. What is common in these three? Dx, dy, dz is common. Correct? Here also dx, dy, dz is there. Here also dx, dy, dz is there. Here also dx, dy, dz is there. Therefore, dx, dy, dz will become common. That into dou ax by dou x plus dou ay by dou y plus dou az by dou z. Is it not? That is what we are getting here. Closed surface integral of a dot ds is equal to dou ax by dou x plus dou ay by dou y plus dou az by dou z. Now, what is our volume, students? Volume is given by dx into dy into dz. Dx into dy into dz. That is the volume. Length into breadth into height. Correct? Therefore, this is our volume. Now, if I take this volume, this is delta V to the LHS. This is dou ax by dou x plus dou ay by dou y plus dou az by dou z into dx dy dz. If I take this multiplicand term into dx dy dz to the LHS, it will come to the denominator. It will come to the denominator. Therefore, closed surface integral of a dot ds divided by delta V. Now, if I apply the limits, okay, because it's a volume here, if I'm applying the limits, because it's a divergence, it shrinks to 0. Volume shrinks to 0. If I apply the limit, then it will be limit as delta V tends to 0. Closed surface integral of a dot ds divided by delta V, that is equal to dou ax by dou x plus dou ay by dou y plus dou az by dou z. Okay. In other terms, we can write it as, we can also express this as, okay, that is closed surface integral of a dot ds. What is divergence? Divergence is del dot a. Divergence is del dot a. Correct? So this is del dot a. This term dou ax by dou x plus dou ay by dou y plus dou az by dou z is del dot a. Correct? It's a divergence of a. Then if I take the delta V to the RHS, if I take this delta V to the RHS, it will be delta V, that is divergence of A, delta dot A, students, delta dot A, divergence of A with respect to the volume delta V. I hope you all are following here. See here, dou ax by dou x plus dou ay by dou y plus dou by dou z of az. This is del dot A, divergence of A, this term, RHS term. Okay, if I take this delta V, which is in LHS denominator, to the RHS, then del dot A with respect to delta V, del dot A with respect to delta V will be the RHS. Correct? Now, what it indicates here, students? Therefore, if it is delta V, then I have to, it is del dot A with respect to point A. If I want to get the entire, with respect to entire volume, I have to integrate that. Correct? That is, the closed surface integral of the vector A with respect to ds is nothing but the divergence of A with respect to the volume. This is a very important statement. What it says, the closed surface integral of the given vector with respect to ds is the divergence of A, okay, is equal to the integral of divergence of A with respect to the volume, with respect to the volume. That is, if I take a closed surface, if I want to find the total flux that is coming out of the surface, by taking, suppose if I take some closed surface, it may be your sphere or it may be your parallelepiped, okay, rectangular closed surface, it may be any closed surface, right? And if I want to find the total flux that is coming out from that surface, then that is nothing but, if I consider a point, some point in that surface, in between in that surface, and if I integrate the flux from that point over the entire volume, then both are one and the same. Yes or no? See, the flux coming out of the surface, that is nothing but total flux or the net flux coming out of the surface, that is equal to, if I integrate the point, if I take some point in that closed surface, and if I take the divergence means spreading factor, which spreads out in all the directions. If I take the divergence of A at that point, okay, at that point, if I integrate that divergence with respect to the entire volume, so that is a point. If I integrate with respect to volume, what it gives? The total flux. Both are one and the same. That is, integrating the vector A with respect to the surface will give me the total flux, if I integrate the divergence of A with respect to the volume, that will also give me the total flux. Both are one and the same. So LHS is equal to RHS. This is called as the divergence theorem. Divergence theorem. Clear here, students? So what is divergence theorem, students? Yes, please. Who will tell me the statement? Divergence theorem. Yes, please. Divergence theorem statement. We started with the definition. Then we considered the closed surface, a point in a closed surface P. Okay. Then the total. Yes, please. Any question? Okay. So we considered the. Please mute your cell phones. Mute your cell phones. The closed surface integral of A dot ds, that will be total surfaces, that is front, back, left, right, top and bottom of the vector A with respect to ds. Then a three-dimensional Taylor series we are using in order to find the total flux or the vector field A about the point P. We are expanding that using the Taylor series. This is our Taylor series equation, right? Then you may ask me what happens to the higher order terms. If I take higher order terms, as I go to the higher order terms, they will get neglected. Okay, because what will happen if you take derivative of square terms or derivative of third derivative, second derivative, fourth derivative. If you go on derivating higher and higher order terms, they will be very less. They will become negligible and then they will be neglected. That is why we are neglecting these higher order terms later when we are adding them. Okay. Then we take for the front surface, for the front side. Then we're writing the coordinate in terms of x is equal to x naught plus dx by 2 and ds is equal to dy dz, that is dx. X is equal to x naught this plus this half dx by 2, then area will be dy dz into the unit vector in the other direction, that is x direction. Ax magnitude is 1, we are not considering that. Then when we integrate that, we get dy dz of, that is ax of x naught comma y naught comma z naught plus x minus x naught will be dx by 2 into dou ax by dou x at the point P plus higher order terms. Similarly, for the back surface, it will be x is equal to x naught minus dx by 2, ds is equal to dy dz into minus ax because it's the opposite side. Then the back surface A dot ds is equal to minus dy dz into ax of x naught comma y naught comma z naught minus dx by 2, because x minus x naught will be minus dx by 2 into dou x by dou x at the point P plus higher order terms. Then I am taking front surface plus back surface, will get dx dy dz common into dou x by dou x at the point P plus higher order terms. Similarly, for the left and right surface, dx dy dz dou ay by dou y at the point P. Then top and bottom surface, dx dy dz dou az by dou z at the point P. Then I will add the three equations, whatever we are getting. Then we are taking the closed surface integral of A dot ds, that will give the common term dx dy dz multiplied by dou ax by dou x plus dou ay by dou y plus dou az by dou z. Okay, what is dx into dy into dz? Length into breadth into height, that is delta v. Delta v. So if I take this delta v to the LHS, it will be limit as the closed surface integral A dot ds divided by delta v, as delta v tends to 0 is equal to this. Then the RHS is nothing but our divergence of vector A, del dot A. And delta v, if I take it to RHS, it will be del dot A with respect to delta v. That is, if I integrate the vector A with respect to surface to get the total flux, that is nothing but as good as integrating the divergence of the vector A with respect to the volume to get the total flux. Okay, and this is called as the proof of our divergence theorem or the divergence theorem. In examination, if they ask write the definition of divergence theorem or write the statement of the divergence theorem and derive it, then you have to start from here, the basic definition. Okay, draw this figure, write the various equations, this basic equation, start from here, Taylor series expansion, and the other equations, and finally mute your cell phones, please. Mute your cell phone. So this will be the divergence theorem. Okay. Hope you all understood here, students. Any difficulty here? Students, are you able to listen to me?
Yes, sir.
Hope you understood here. Yes.
Yes, sir.
Okay, fine. Karthik Patil,
Yes, sir.
was it understood? Okay. Vishal
Yes, sir.
Bhosle,
Understood.
good. Vishal Bhosle, Pallavi Dharegowda, Pallavi Dharegowda. Okay. Rohan,
Yes, sir.
understood Rohan? Today's derivation.
Yes, sir.
Okay, fine. Sohail Syed, Sohail. Okay. Ankita,
Yes, sir.
understood Sohail?
Yes, sir.
Okay, good. Ankita,
Yes, sir.
Ankita, was it clear derivation, Ankita?
Yes, sir.
Any questions, any difficulty,
No, sir.
any problem in understanding, Ankita, the derivation part?
No, sir. Understood.
Okay, fine. Okay, students, then I will let you know when will be the next class. Okay, we'll stop at this moment. Then in the next class, I may continue with that is your Coulomb's law, whatever you have studied in your PU level. Okay, the force acting between 2 point charges, which is given by the product of the magnitude of the two charges divided by distance square. Okay, we'll start from there. That will be our next topic. Okay, then meanwhile I'll give all the assignment also. Assignment questions will also be given. Okay, thank you, students.